First off, who might uh, who might be interested in this talk, so that if you don't fall into that category, gets lunch. I think folks that might be interested in this are either someone curious about the organization of the existing NorthStar driver for SteamVR. Perhaps if you're working on another project that also coordinates a bunch of different sensors, or if you're interested in a quick, very high-level overview of the current distortion solves that are available for the NorthStar. Perhaps interested in how SteamVR consumes various data points, particularly hand pose. That's lightly documented. Or if you're thinking about adding or extending this driver with other sensors or other experimentations on it. Or of course, anything else that sounds like it might be adjacent to that. So to start off, I'm going to give a very brief overview of the structure of a SteamVR driver. SteamVR expects you to register a factory with them, and when they start up, that factory creates a server. The server's job is to manage resources that are required for your driver and notify the runtime that, hey, I found an HMD, I found a controller, and it's ready to start being used in experience. That controller or HMD are what SteamVR refers to as tracked devices, and they can supply various things like the ability to output rendered pixels of a scene, provide input such as buttons, button presses, triggers, or skeletal pose information, which is also considered input by Steam. They provide a raw pose as part of the track device thing, but it could just be a puck. And a model to represent it in a VR experience, so the user can find it. There's another component called the watchdog component that protects people from bumping into objects in their home or walls. Considering the NorthStar is an AR device, avoiding objects is left up to the user. And I saw go into like kind of an overview of like things that are a little bit more complicated in the NorthStar driver were different from this flow. Starting at the server is it's not very different, but it's an overview of some of the objects that are not necessarily straightforward from seeing their names. The NorthStar server has an HMD it provides, which represents the actual headset with pose information and distortion and all of that. And it can optionally provide controllers. Some requests came in to disable the tracked hands if folks wanted to use like some other controller method to provide pose when their controllers are behind their hand or behind their head, or whatever other use case. There's an optics class in there which encapsulates the two different configuration methods that are available for Project North right now, which are referred to as the 2D solve and the 3D solve. And then there's a class called the sensor frame coordinator, which deals with interdependencies of sensors and kind of encapsulates all that. And then a parameterized class for whether you're using a real sense or a structured core to kind of understand the world around you. The last kind of main thing in there that is sprinkled everywhere are these like spatial adapters or world adapters or vector or matrix factories. And those were kind of an experiment. When I was making this, I was a little worried about the performance drawbacks of making these calls to these other adapters in kind of critical code. But they seem to perform fine in a release build. And I'll have more to say on them in kind of like the what went well, what went bad, our takeaways. I'm going to dive a little bit more into the sensor frame coordinator, the two different solves, and then kind of these spatial adapters and their trade-offs. Starting with the frame coordinator. The role of this object is to kind of take away some of the interdependencies of frames from sensors. The sensors themselves all provide their most recently received data about pose or skeletal position, stuff like that, through their own kind of classes that run their own threads and cache the most recent one there, as well as like, do I know where I am in the world, or have I lost my position, stuff like that. The frame coordinator caches the most recent pose provided by these threads, which is provided every frame, and simplifies the logic like, I have a hand pose, but I don't have an environment pose, so I can't really say where the hands are because the leap motion sensor is attached to the head, and the head could be anywhere. So that the rest of the code base cannot worry about it and just ask for hand data and maybe not get it. Next to the optics, this is a really straightforward class to hide whether the user is using a 2D distortion solve or a 3D one. I'm going to try to give an overview of the 2D or 3D solve methods. Hopefully it's not redundant with another talk. And this is my current understanding of them. I consumed these, but I didn't have much to do with the development of them. So apologies if I get some of this off. The 2D solve overview is newer. It's dependent on, the 2D solver is newer. It's a little easier to do, but it's dependent on the RealSense sensor to gather data, which is perfect if you have one of the newer headsets because you have one already. My understanding of the basics of how it finds the solution is it projects a known image off of the displays of Project North, and those are reflected by the reflectors, and the camera positioned approximately where an eye would be fits a 2D polynomial to kind of undo the distortion perceived by these. From the driver's side, consuming this is really straightforward. You, given a UV, plug it into the 2D polynomial and give the result back. The 3D solve is a little bit more involved. I've also haven't really interacted with it in almost a year, so bear with me here. The general idea is you have two ellipsoids that represent the reflectors. Imagine a scene where the NorthStar is in the scene with ellipsoids representing the reflectors, quads representing the screens, and two objects where an eyeball would be. It fits those as best it can to the real device that's being used and writes that data out. In consuming this, it's a little bit more involved. You shoot a ray out from where the eyeball is. Try to intersect that with the inside of one of the ellipsoids representing a reflector. Get the bounce from that if it intersects, and then attempt to intersect that ray with the quad representing the screen that you're trying to do the solve for. If that all intersects, you can use the delta between where in the display you hit in the scene versus what position on the display you're attempting to hit with this ray, and modify it iteratively until you get within a delta of the target. Okay, that's everything there is to the driver, pretty much. These spatial adapters I think were really the brunt of the work, or I guess space itself was the brunt of the work, and also debugging. I think by far this project has given me a newfound respect for being very specific about when spaces are transitioned between and exactly what those spaces represent. And this is a perfect time to go into what went well, or what some of the takeaways I thought were, and then what went bad, and maybe what's next. For what went well, I think it's a pretty straightforward thing to do, but isolating the service communication in their own threads and caching those made that very straightforward to kind of mock out when testing, as well as made when there's a different environment sensor pretty straightforward to add and configure during driver initialization. The sensor frame coordinator did a really good job of both isolating the sensor dependencies, as well as offering another good hook for debugging and testing to provide some fake scenarios. Same thing about debugging and testing with the optics abstraction. Like I said before, the spatial adapters and vector factories, I was a little concerned about the performance with them. In release builds, I didn't notice anything. The debug builds are quite slow, though. I suspect it has a lot to do with these calls. But they, again, provided a really good isolation of, well, they provided two things. There was very explicit statements in logic that didn't really need to be concerned with space conversions of what spaces we were going, what spaces were being transitioned between, like from and to. It also hid the details of doing that from whatever was more interesting that was going on in the function. And I think a big win that I didn't do, or a big takeaway that was went well, that wasn't very straightforward to me, at least on initially doing this, is hooks to force these various components into very well-defined positions. Like just put the HMD straight at origin, put my palm right in front of the camera, and then I'm just going to stare at fingers and see what's going on there. The support utilities, I had used Eigen before, but not to this extent, and it was really performant, and it was really descriptive of what was going on in MatrixN, much more so than my interactions with things like GLN or custom rolled kind of struct matrix implementations. It does a lot of really neat tricks to delay computation until the last minute it's needed and take advantage of any hardware that's there. I would definitely recommend it to anyone that's doing C++ 3D math. There is a drawback of it that it requires you to use auto to get some of the delayed computation, and that can make it put a lot of the onus on variable naming to convey what these objects represent in the middle of computations. All these support libraries are header only, so just want to make sure to mention that. I tried out Trompe Loyal, which is a mouthful to say, but it was a really straightforward way to mock objects with very low effort. And doctest was great for behavioral driven tests. I'd also recommend those. So now, kind of maybe the more interesting thing, what went wrong? Or what could have gone better? I was more optimistic when I wrote this. I chose to go with the native SteamVR configuration stuff. And I think that ended up being a big drawback in that it was pretty restrictive. You can't have deeply nested objects in it. So you'll notice if you do go into the configuration, there's a bunch of kind of name mangling in subkeys, and they really should be objects under like just another object in there. But SteamVR just doesn't support more than one layer of nesting. It was another barrier to people who were kind of trying to set this up. It was a opportunity for human error, copying from that JSON file to this configuration. It was more work for someone trying to do that. And as a side effect, even though this is like implemented in a configuration class, it would have been much better just to consume a JSON file in there and maybe read that from the Steam configuration. So I think that definitely could have gone better as a pain point. The installation is rough, and I think this is a problem every Steam driver that isn't shipped with Steam has. Steam offers a binary that you can use to register drivers called VR path reg, but that's in wherever the user installed Steam. And at least for me, I almost never install Steam in the default place. So it's hard to rely on where that will be on the host machine. So and it's also not added to the host machine's path. So that's another barrier that someone trying to use the driver has to go through, where you need to provide tooling around. And I can't think of a good platform agnostic way of providing that tooling. The last thing that could have gone better is definitely space. Space is hard. And I think particularly when I'm guilty of this too, and I'm not trying to throw any shade, just a real kind of takeaway for me was how important it is to be very explicit about space. It's easy when you're working in just one space all the time to say things like, oh, this is the screen UV, or this is world space. But is that world space GL like? Is it Unity like? What is forward? What's up? What's right? When you're talking about screen space, what is 0, 0? And all these things vary. And in many parts of this, they varied quite a lot, and in ways where it kind of required some investigation to figure out what was going on and what the intended one was, kind of like taking the device, fiddling with it, and saying, oh, okay, well, that's right-handed. That's all stuff that we as a community could do more detailed work on. But like I said, I'm trying to throw any shade. I wrote this whole thing and there's no documentation, so I'm not someone to talk. It was just definitely a pain point. Again, it came up in the skeletal data representation that Steam has. The file format that is in doesn't have a strong definition of what forward is for a bone. And I remember in like digging into it, I noticed Steam mentioned, like in the docs somewhere, they mentioned Maya, and I went to load it in Maya, and you need a licensed version of Maya to really dig at the information I needed, or I couldn't find out how to do it that way. So I ended up using Blender. Blender has options on importing where you can dictate what forward is, or it can try to guess, because it's not written into the spec for the skeletal format. And things like, are the bones in their parent space? Are they in world space? Are they in the controller space? All those things that are easy to forget need to be explicit if someone else is consuming this data or working with it. I don't know how I'm doing on timing. 15 minutes, 10 minutes. I think there's anything else on space here. Something in particular, the Leap Motion docs were amazing with their space documentation. Just a shout out there. This was great. Not only had what everything represented, but they were nice enough to include conversions between their spaces and popular engines and things like that. It's great. What might be an area next? Like what might be an area to improve the driver, or what could be done with it further? I mean, it works as new sensors come. I'm going to keep maintaining it and adding those to it. I think an interesting thing that could be added or experimented with that I initially wanted to, but I didn't really have the time or energy at the end of the project, was to take these hand poses, which are set up to kind of be fed into another object that could recognize or work on a time series of hand poses, and either use machine learning or whatever else, just raw analysis, to do some gesture recognition or anything like that. And I guess last, a little bit about me. Here's my contact info. If you're going to be working with this code or have a question about it or anything else, feel free to reach out. I'm always happy to talk. I'm currently working on a AR mesh network to help folks and different devices kind of interact in the same space in the real world. That needs about another month in the oven, but I'm working on real bindings for it right now. I eventually want to open source it, and I would love to collaborate with anyone interested in either making some initial experiences, or you might have feedback from whatever your profession is or anything like that. I think I don't know if I went really fast through that. I think I'm 10 minutes short, but I'm happy to answer questions or anything else. I hope that was useful to anyone listening. It's kind of very mechanical. I don't think there aren't really very interesting, like, tricky problems that this driver solves, but hopefully those takeaways and learnings will be useful to someone. They're rough, I think. I mean, I didn't prepare by refamiliarizing myself with them. I've been in a different space altogether working on this mesh thing. But I think that was another area where the biggest barrier was kind of just not very good or straightforward documentation. Like, eventually, and that might be good findings to share too. There are tools that make that less painful, but the tools aren't really pointed to anywhere in the documentation that I've found. I was fortunate enough to have Joe's ear, who works on SteamVR, and he kind of shared this tribal knowledge directly. But I'm blanking on the name of it. I'll put it in chat. There's a binary that ships with Steam that dumps raw pose information from devices, and there's also a lot of developer related tools that are in the bin folder for SteamVR that do things like allow you to look at overlays or debug bindings or configure them from outside of VR. And all of those were really useful in kind of trying to fiddle with what's a good sensitivity for a button press when you're using your hands. And honestly, and that's more work too. I think that's why gesture recognition, I was thinking, would be another way to improve the driver. Using raw sensor data from the Leap Motion device, it was hard to get everything feeling good with pressing buttons. I think the most reliable gesture I was able to get down was kind of a Spider-Man like web shot or clicking a button. There's nothing in there right now that does pose prediction, but you could, if you fed these skeletal poses into an object that's either owned by the frame coordinator or the controllers themselves. I think that's another area that could be fun to experiment with. There's a lot of, and this is almost a year old research right now, but when I looked at it, there were a lot of nets that were pretty performant and did pose recognition, like pose prediction. Sorry, not prediction. Well, I guess prediction is an okay word for it. Extrapolated pose from occluded fingers and stuff like that.
So I'm just going to take advantage of the fact that I own this Discord server to just ask my question in voice. YOLO, right? So I guess my question is, moving forward, we've definitely, I think we've discussed a little bit about our different platforms today in various talks and stuff. But I think one of the things that's sort of missing right now in our structure, you mentioned, coordinate frames and testing and stuff. I think, realistically, we could build some tests that would allow us to confirm whether or not the systems are reading calibration data correctly among like either SteamVR, Unreal, Unity, Godot, etc. And I think that would be really useful. But it does look like there's another question in the stomach channel as well that could be answered. So
yeah, I think that would be really useful, especially from the standpoint of someone who might be making playing around in this like space with the North SDK and everything. And there's another layer to that where the NorthStar screens are upside down as well, and some like it's just another thing to call out that isn't always there. Yeah, I can if you want to talk after, or we could do it in this channel. I kind of troll the ML white papers around this stuff from SIGGRAPH every year, and it's pretty common now for them to, along with the paper, release a Git repo that not only has the weights with it, but also has the exact PyTorch code, whatever they used to implement it. And from there, you can then use a C++ implementation for that network to run data in and out of it. I would definitely recommend trying to get something that can be converted to PyTorch and consumed by that, because building the wow, I'm blanking on the other big solution for ML. It's by Google. It's the one that's actually, I think, better known. But their C++ library is dependent on Python and dependent on a bunch of other things, built in a weird build system that is really hard to get to work right. And I did it once for this one project, but it's really hard to get a static lib out of it and consume it. TensorFlow, yeah. They have a C++ solution for their networks, but it's really hard to build. And most networks can be converted into another format pretty easily. And those are very straightforward to build and link against on different platforms, even if you don't have access to something like CUDA all the time. Or at least that's been my experience with them as of half a year ago. So might have changed.
Well, so have you done any work with looking into SteamVR's OpenXR implementation? Does the driver currently support that, or is that something that we would need to change?
No, it works one-to-one. I haven't looked at that since I started this kind of mesh network thing, but it was just a drop-in replacement. I've done some XR development against TeamXR, and all the old drivers work. They kind of made it a transparent transition, and you just use the newer API against the same stuff.
That is super exciting.
I haven't tried any of this on Linux, but it should all work. I think there's a missing function to identify the display of the NorthStar that's if-deffed out that someone would need to write. But on Linux, you have Monado, which has other NorthStar drivers for it too.